Hello everyone. In this video, we are going to look at the test for the induction motor and what kind of test can be done to take out the parameters, the parasitics of the induction motor. We have typically we have three kinds of tests for the induction motor. The first one is the DC test. The second one is the locked rotor test. Yeah, I should change the order here. Yeah, the DC test is normally done in the beginning, and then afterwards we do the locked rotor test. And the locked rotor test is very similar to the short circuit test in transformer. And finally, we have to do the so-called low test or free running test. And this test is very similar to the so-called open circuit test in transformer. And to begin with, right, let's talk about DC test first. You can do the DC test very easily. Yeah, you just pick up two terminal of the induction motor and then measure it using the multimeter, or more traditionally you can use the CT to measure the current and the voltage, the voltmeter to measure the line voltage. So now the actual resistance that you are going to measure is the winding resistance, and there will be two winding resistance connected between one line and then another. There will be two winding resistance. This means two R1. So in other words, you can calculate the Y connected winding resistance by this formula. And on the other hand, if the motor is delta connected, then you need to multiply the whole expression by 3. And the second test that we are going to look at is the locked rotor test. Locked rotor test is very similar to so-called the short circuit test. So what you need to do is you reduce the adjustable AC voltage by lowering the voltage magnitude and also the frequency. You cannot use the rate frequency because the rate frequency is too fast to be manually manageable. So what we could do is to lower the frequency to a value that we can handle. So if the line frequency is 60 hertz, 60 hertz is indeed too fast for us. So what we can do is to lower it to somewhat 25% of the rate of frequency. So I have already highlighted here. The locked rotor test is conducted at 25% of the rate of frequency normally. And the voltage should be lowered as well, because when the voltage is too high, then the safety equipment and all other measuring equipment have to be has to be able to withstand so much voltage. And to test the rotor, then we keep the shaft of the rotor stationary. So we don't let it spin. We just hold it to stand still. And then we measure the line voltage and the line currents. And more importantly, we measure the wattmeters. We measure the wattage of the motor. And finally, we take down the reading for the voltage, current, and the power. The voltage is most likely the line-to-line voltage. The current is most likely the line currents. And finally, we also need to perform a free running test. Free running test is also so called the low load test. And to do this test, right, you need to adjust the source voltage to the rate value. And the equivalent circuit of this low load test is like this. We don't have any elements about the rotor in the equivalent circuit because the load test is equivalent to the open circuit test. So in this case, the current will be going through to the status winding and also the core. And we also use the rate frequency. So if the power supply is running at 60 Hertz, then we should use 60 Hertz. And if the power supply is the phase voltage or the power supply is 220, then we should use 220. And in a free phase situation, if the phase voltage is 460, then we should use 460. And we measure the current, voltage, and power. Okay, and we can use the same test instruments as we did for the locked rotor test. I mean, it's the same emitter, same voltage, and same power meter. Now, the test looks very simple, deceptively simple, but to take out the parameters based on this test is not going to be easy. Yeah, the purpose of this test is to find the parasitic of the core, which includes the core resistance and the magnetizing impedance, the magnetizing reactance. And this is just my suggestion. You may have better methods. So what I normally do is I find out the line current first. At least, right, we have already got the magnitude of the line currents. So what we need to do is to use the power, phase voltage, and the line currents to calculate the phase shift based on this formula. And the phase angle in this formula is theta. the phase angle is normally negative. And with this in mind, we can calculate the voltage E2 here. What we need to do is to use the phase voltage and subtract it by the voltage across the R1 and X1. So is the line current, the phasor form of the line currents multiplied by R1 plus JX1. So this is going to be the potential difference across the winding impedance. And then the voltage E2 should be without the potential difference across the winding impedance. Now finally, the E2 will be in a complex phasor form, and same for the current. And what we can do is we use the complex value of the line currents and the complex value of the phasor E2 to calculate the admittance here. So what is going to be I, the phasor form of the line current, I, and then divided by the complex form of E2. So from there, you got the admittance, and you can use the use the real part of the admittance here to calculate the core resistance RC, and you can use the imaginary part of the admittance here to calculate the magnetizing reactance of the core. It looks complicated, but I'm going to show you an example. The example is here, and we have a 3-phase induction motor, Y connector one, and the rated power is 60 horsepower, and the rated frequency is 60 hertz. The rated line voltage is 460 volts. The rated current is 57. This value is normally not very useful. And we have done the following tests. The first test is the DC test. And in here, the DC voltage and current are given here. And we all have also done the locked rotor test. And here, the locked rotor test is running at the locked rotor test was conducted at 15 hertz. So bad grammar. Was conducted at 15 hertz. And we also have a low test. And remember, normally in a low test, we adjust the voltage to the line voltage. So if the line voltage is 460, then the voltage to be used for the low test should be the same, because eventually we want to obtain the synchronous speed. The sleep, we want the sleep to be 0. The line current should be the rate one, but it depends on the situation. Then the power here is the value measured by the wattmeters. And the rotor reactance depends on this test, and also it depends on the design criteria. So if we assume the rotor test to be 0.6 times of the total reactant, like in this case, then eventually we need to do such and such adjustments in our in the answer to this problem. And then we determine the motor parameters and draw the equivalent circuit. So let's go. So I'm going to switch you back to the whiteboard mode. So now you are looking at the whiteboard here, and this is the question from the previous slide. And the wording here is exactly the same. I've not done any change on this. So let's go through each element and find out the motor parameter. As I said, normally we conduct DC test first. And in the DC test, the voltage and current is in this value. So the voltage and current should be equal to a resistance, which include two winding resistance. So V1 here is 12, and VDC is 12, IDC is 59. So 12 and then 59, and then to allow one. And if you do it carefully, then you will get exactly the same value here. Now, this one is done. Now, the next step is to analyze the blocked rotor test. So, blocked rotor test. Blocked rotor test. And we have this value, and the equivalent circuit for the locked rotor test is like this. R1, and then JX1, and then we have a resistance R2, and then reactant RV. So JX2. The current here is 52. So let's calculate it. The voltage should be the phase voltage. The voltage here is given as a line voltage, so we need to convert it into better write down everything. Vline divided by root 3. So you get this value here. And now we are going to calculate the impedance. And the line current here is just the magnitude. You need to find the, the phase angle for this current. So what we can do is, right, we write down the power. Say this is the log the rotor test, right? P uh, L R, sorry, yeah, L R, and then this one is like the PV1, and then I1. Yeah, this is the magnitude, so we don't need to do anything. By the way, like this is the magnitude, right? And then cos beta. And according to the equation here, um, we have 204 in the left hand side, and then we have this value, and the line current is 58. Then we got the current, but it's a bit complicated, right? We can use another way to do it. And we have the value here. We don't need to go through this cumbersome step. There is another way to do it. We have the magnitude of the phase voltage and the magnitude of the I1. So all we need to do is to find out the magnitude of impedance here. And the impedance here should be equal to V1 over I1. And in this case, V1 is going to be 36.2 divided by root 3. And then the current here is 58. So this way is more elegant. Uh, If you do it carefully, uh, you will get a value 0.36. But this log to rotor test is done at uh, 15 hertz. So the um, it's okay. Yeah, leave it. And we are going to calculate based on this formula. You know, Z here square is equal to R1 plus R2 square plus X1 plus X2 square. So we still need to find R2 in order to calculate, in order to solve this question. So what we can do is to calculate R2. And what we can do is based on the power and the line current, and we found out the resistance, the total resistance. So the line power is PT, right, which is equals to uh, 3 times I line square. And then the total resistance in this circuit is R1 plus R2. Resistance is the only element that would consume power. The uh, the power here is 250 2,573.4. The line current here is 58. So if you do it carefully, you will get the value for R1 and R2 combined together. Uh, let's see. 0.255. And if it is the case, R2 is going to be this value minus R1. R1 is 0.102. So eventually, you should get you should end up with a value very close to this one, right? So now we found R2, and now with the knowledge of R1 and R2, we should be able to resolve this equation. And Z is going to be 0.363 square. And uh, uh, the total resistance here is going to be 0.255 square. And then now we got the value here, and we are going to solve this equation for x1 plus x2. So if you do it carefully, you will find that this value is x2, xt, oh, 0.2546. And now this is the reactant calculated at 50 hertz. So eventually we need to adjust this frequency. The frequency is going to be this value, times 60 divided by 15. And the value that you would get is 1.01 84. So now I'm going to clean up the board. Uh, I just need this value. According to what we have just done, x1 plus x2 is equal to 1 point. And the rotor reactant is observed to be zero point 0.6 times the total reactant. In this case, x2 is going to be 0.6 times this value. So the answer should be more or less the same here. Let me check. Six one one one. And x1, according to this equation, is going to be 0.1 times minus x2. And the value here is going to be 4.074. So right now, x1 and x2 has been done. And finally, we are going to switch to low test, no low test. And do not forget that the equivalent circuit for this test is like this. Uh, and then the voltage here is E2. The inductance here should be XM and RC. The voltage, again V1, and the current I1. So we are going to use the information from the question with the help uh, of the equivalent circuit. We are going to find out the circuit parameter and most likely, right, to find out the RC and XM. The answer, given the answer from the question have only XM. So we need to find out what's going on. Uh, First of all, we need to find the compact phasor of the current. Right now, what we have here is the magnitude. This is the magnitude, and this one is also a magnitude. Of course, right? The power is the magnitude. So first of all, the V1, the magnitude of V1 is 460 divided by root B. Most likely, this is going to be 265.8. The current is given here. The current is 32.7. So based on this equation, based on the power here, we can find out the phase angle between the current and voltage. And P is going to be 3 V1 I1 and then cos theta, where theta is the phase difference between I1 and V1. And if we substitute the value into this formula, we get 265.8, 52.7, and then cos beta. And if you do it carefully, beta is going to be 1.39 radian. And in this case, the angle here should be negative. And the current is going to be, the phasor form of the current is going to be 32.7 and then 1.39. I'm not sure whether you can see the right one. So this is the current. And now our job is to find E2. This is the next thing that we need. We know the current, that's good enough. We know the current and we know V1 and the winding impedance. Then we can use this information to find E1. E1 according to to this diagram here. Is V1 minus the current here, I1, and then R1 plus J1. And we have already got the value for V1. It should be this one, right? This one. Through 65. And I1 is a complex value. It's typical for me to write down everything. And then times the reactant here. The reactant is given by this value, right? 0.102 minus plus J and X1, right? 0.4. So if you do it carefully, then you will find out the phasor for E1. The phasor for E2, the value is quite complicated. And what I'm going to do is to write down the phasor, the complex value of E2 here. Yeah, let's see if you can see the right one. Okay. So E2, according to my calculation, is 25187 and 97, and then plus 0.8868. So this is your value. And do not forget that, right? I1 is according to here. And then some complex value. So what we can do is to find out the admittance of this equivalence. We don't find the impedance. Instead, we find the admittance. So the admittance here is YC. We can find out the admittance with the knowledge of E2 and I1. So all we need to do is to find the ratio of I1 to E2. So let's continue. YC is going to be I1 over E2. So you have to use GNU Optics or Matlab to work this out. It's not going to be easy. 251. So eventually, you will end up with a value The value is 0 on the real part of the admittance. Here is 22793, and the imaginary part is 0.107. Okay. So if you do it carefully, then you will get this value. And I have already told you before, the real part will be able to yield the RC. RC is 1 over the real part of YC. So in this case, it's going to be 1. And if you do it carefully, I can tell you the value here is 40 something, 40, 43.9. Let's write down more clearly. And the magnetizing reactant is 1 over the imaginary part of YC. So if you do it carefully, and you have the minus here. According to my calculations, the value here is 11.82. So the answer is somewhat slightly different from this value. Maybe the way of solving the problem is different, so I don't care much. If you have any questions, please leave your questions to the comments box underneath the video. And thank you very much for your support.